Hi all. In this section we can discuss what are the different types of stresses acting on mechanical materials. The various stresses are tensile stress, compressive stress, bending stress, direct shear stress, torsional shear stress, bearing pressure, crushing stress, contact stress. Then we can discuss each one separately. Tensile stress. When a mechanical component is subjected to two equal and opposite axial pull, then the stress induced in it is called a tensile stress. Normally, we can take example for a connecting rod. As shown in figure, there are two forces, that is axial pull happens on that connecting rod. It is denoted as capital F, and we need the cross-sectional area, that is denoted as AO. Then the stress is equal to F divided by AO. Next one is compressive stress. When a mechanical component is subjected to two equal and opposite axial pushes, which means the pulling, we can see it in our figure, that is there is a force named it as PO on the two sides of the shaft or connecting rod. The stress induced in it is called compressive stress. For example, connecting rod, links of structure, columns, etc. This type of compressive stress will happen. And next one is bending stress. When a beam is subjected to a bending moment and denoted as capital M, the stress induced in it is called bending stress. As shown in the figure, M is shown on the bottom side of the first figure. In this section, there is a combination of tensile and compressive stress. That means on the bottom side of that first figure, compressive stress will happen, and the top side of that figure, tensile stress will happen. So there is combination of compressive stress and torsional tensile stress are here. We can find the equations. The bending stress can denoted as sigma b is equal to m into y divided by I, where sigma b is the bending stress and the unit will become Newton per millimeter square. M is the bending moment for the section cross-section area AA, and I is the mass moment of inertia. Then y is the distance of fiber from neutral axis. So we can use these values in the equation sigma b is equal to m into y divided by I. If it is y max, we can take the value y max is equal to d by 2. That is the distance of extreme fiber from the neutral axis, and the sectional modulus is denoted as z, that is equal to I divided by y max. For a rectangular cross section, we can find this value. Let d is the distance perpendicular to neutral axis, b is the distance parallel to neutral axis, and I is equal to, here I is equal to bd cube divided by 12, note this value, bd cube divided by 12, and y max is equal to do by 2. So we can calculate the sectional modulus z is equal to I divided by y max, that is bd cube divided by 12 divided by do by 2. From that equation we can find the value z is equal to bd cube by 6. For a circular cross section, I is equal to pi d raised to 4 divided by 64, and y max is equal to d by 2. Here the sectional modulus z is equal to pi d cube divided by 32. If it is a hollow circular cross section, similarly we can find the value of z using this equation. Then the value will become pi into do, that is the outer diameter, do raised to 4 minus di, that is the inner diameter, da raised to 4 divided by 32 do. Then we can discuss about shear stress. When a mechanical component is subjected to two equal and opposite force acting tangentially, note the point, tangentially across the resisting section, it tends to shear off across the section. The stress induced in such section is known as direct shear stress. The direct shear stress acting along the plane, as the figure shows, it is a rivet joint. So in the right side of the figure, that is in the figure B, we can identify a rivet in the figure, and there are three plates. Below that figure, we can identify if the pull will happen, the rivet will fail due to this kind of stress. That stress is known as shear stress. We can calculate the value of shear stress using this equation. Tau d is equal to Ps divided by 2a, where Ps is the direct shear force acting across the section and A is the cross-sectional area. It will generally happen in rivets, bolts, knuckle pin, cotter, etc. The next one is torsional shear stress. When a mechanical component is subjected to the action of two equal and opposite couples acting in parallel planes, then the component is said to be torsional and shear stress induced in it is known as a torsional shear stress. And we can calculate the value using the equation, that is tau by r is equal to T by J is equal to G theta divided by L, where tau is the shear stress, r is the radius, and capital T denoted for the torque, J is the polar second moment, or G is the modulus of rigidity, and theta is the angle of twist, that is how much it will twist. Then capital L is the length. J is equal to pi d raised to 4 divided by 32. We can calculate this for a circular cross section and hollow circular cross section. So here I max is equal to pi d raised to 4 divided by 64, and the value of r is equal to d by 2. Similarly, for a hollow cylinder, there is two diameter, that is outside diameter and inside diameter. Using this equation, we can find the value of torsional shear stress. Next one is bearing pressure. It is a localized compressive stress at the area of contact between two components having relative motion between them is known as bearing pressure. We can find the bearing pressure using this equation. Consider a pin and I loaded as shown in figure. The actual contribution of the bearing pressure will between the eye and pin, it is not uniform. So bearing pressure we can denote as force divided by project's area of contact, that is equal to P divided by A, where PB is denoted as the average bearing pressure and P is the force acting on the pin, A is the projected area, D is the diameter of pin, and length is the L is the length of the pin in I. Some examples happening in bearing pressure: bush and pin, then power screws, etc. The next one is crushing stress. We can generally call it as bearing stress. A localized compressive stress at the area of contact between two components having no relative motion between them is known as crushing stress or bearing stress. It is a special case of bearing pressure with no relative motion between components in contact. Crushing stress is equal to force divided by project area. Generally, it happens in rivets, nut and bolt, key and shaft, etc. Then last one is contact stress. When two bodies have a curved surface, like two spheres or two cylinder or cylinder and flat surface, etc. are the examples. I can read once more. When two bodies having curved surface are pressed against each other, the point or line, there will be a point contact or line contact. The point or line contact between the two bodies changes to area of contact. The stress developed in these bodies is known as contact stress, or it is known as Hertz contact stress. For example, contact zone of the wheel and rail, cam and follower, mating gear teeth, rolling contact bearing, etc. Okay, So these are the different types of stresses induced in mechanical components, and we have to study the details and the problems on this section. So please study the general behavior of stresses and what are the different kinds of stresses through this section. Okay, thank you.